Good. So I want to welcome everybody to another Earth to class, and today we are very honored to have Dean Jeffrey Shaman from the Columbia Climate School. Columbia several years ago decided that it was important to create a cadre of well-educated people to handle the climate crisis that was looming. So Dean, please tell us about the climate school.
All right, my pleasure. My pleasure to be here as well. I'm going to share my screen because I have some slides. All right.
Okay,
So you
we've
should,
got it.
I'm going to move it into display mode. All right. Do you all see that?
Yes.
Yes. All right. If you have any questions, please just ask ask away. Okay. That way, I may not see you on the screen because of the sharing of the slides right now. All right, so I'm going to tell you a little bit about the Climate School at Columbia University. It's called the Climate School right now with this strapline, Climate, Earth, and Society, because we think more broadly, not just about climate, but climate sustainability issues, the environment, and the Earth. Um, Part of the reason for calling it the Climate School is mandated by what's been happening with our planet's climate, of course, and the planet is warming. I'm going to show you here a figure. This is from NOAA, National Oceanic and Atmospheric Administration. And what it shows to you are surface temperature anomalies for the year 2024. And how these are constructed is they take the measured and estimated temperatures across both the land surface and the ocean surface, and they average it from January through the end of December for 2024. And then they compare this to the average for a reference period, which in this case is 30 years from 1991 to 2020. So they make that same average, but now for that 30-year period, 1991 to 2020, they subtract that 30-year period from the 2024. And if the numbers are positive, that means 2024 was warmer than was experienced in that earlier 30-year period. And if the numbers are negative, that means it was colder. And what you can see is that the average temperature for the entire year for 2024 was warmer over much of the globe, particularly over the land and particularly over the northern hemisphere. You can see going up to the Arctic, it's very warm there. So what we see when we look at the temperatures of our recent year, last year, compared to what happened in recent history, just 1991 to 2020, we can see that there is a pronounced warming over much of the planet, particularly over the land surfaces and the northern hemisphere. We want to look at this over a longer record and in a different perspective. We can collapse those surface records down to a single average. And in this instance, the reference isn't 1991 to 2020. The reference is 1850 to 1900. So the average for that 51-year period is called zero. That's subtracted out, and it's an anomaly of zero for that. And everything else beyond 1900 shows you what the average temperature for that year was over the whole globe relative to that. So if it is warmer, it's going to be positive. If it's colder, it's going to be negative. And there are 5 different estimates of this from different agencies. One is NASA, the other is Hadley in the United Kingdom, along with the University of East Anglia. Another is NOAA, the National Oceanic and Atmospheric Administration. Another is Berkeley National Lab. And another one is a European agency called Copernicus with their ERA 5 estimates. And what you can see is that when you get to the early part of the record on the left, there's some disagreement in the estimates and reconstructions, and that's because the instrumental record was more sparse. There weren't as many stations, there weren't satellite estimates, so it's not as complete. So the estimates of what's going on over, let's say, the Southern Ocean and the Pacific are less well resolved. And so there's some disagreement as to what it exactly looks like, but you can see that the wiggles often match and the disagreement isn't that pronounced. And then as you moved into the latter half of the 20th century, they really start to move in greater lockstep with one another because there's greater instrumentation. In the late 70s, satellites really come online. And so that allows for a more critical and consistent estimation of what's going on. But what's also clear is that despite the disagreement, we can see clearly that there was a rise in the 30s and 40s. It started to go down a bit. And then around 1970 it turned, and temperatures started to go up, and they've been going up considerably. And the estimate is that last year was more than 1.5 degrees warmer than the 1850 to 1900 reference. This is another way of looking at those temperature records, and this shows you the global mean temperature anomaly and its uncertainty. So that anomaly is the same thing that you see here. How much warmer is the temperature in a given year relative to the 1850 to 1900 average? But now, rather than just showing you a point, it's showing you how uncertain they are about that, given that we can't measure every spot of surface that there is on the planet, including all the oceans, right? And you can see that there were some disagreements, even in the later years, among those various agencies. So this actually shows you the uncertainty. And what you can see if you look in the middle is that the block from 2015 through 2021, all the years are there. And they're about 1.15 to 1.4 degrees Celsius warmer than that 1850 to 1900 baseline. And that block of years, that decade, well, less than a decade, is considerably warmer than what happened earlier. And you can see this if you go back to this plot right here, and when you can't see where my cursor is, but at the very end, you can see a shoot up for the last 2 years, 23 and 24. And before that, you see that the years are all bouncing around 1.2 to 1.3, et cetera. And you can see that that's where that is, and that there was a departure from where it had been, which was less than 1 degree warmer than 1850 in the previous years. That's what you're seeing here. You're seeing that it moved up. And this came after what's called an El Nino event in the Pacific, which is a warming of the eastern and central equatorial Pacific. And that tends to coincide with a jump in the planet's warming signal as it sort of ventilates the ocean and increases atmospheric temperatures. We had another one of those take place in 2023, and you can see it's an even larger jump. And you may have heard about this in the news. You may have heard that in June or July, we were suddenly recording average global temperatures that were 0.3 degrees Celsius higher than what we had seen in the previous record, which is considerable. That's a big jump. And that extended all the way through 2024, which, given that it was for the entire year, you can see that it's warmer on average. And you can see the estimate there is a little bit more than 1.6 degrees warmer than that 1850 to 1900 average. Excuse me. Now, the drivers of this are thought in large part to be due to atmospheric greenhouse gases. And these are gases, trace gases in the atmosphere that affect the radiative balance of the Earth. And they do this because they are called what's known as selective absorbers, meaning that they do not interact with the incoming solar radiation, which is at a higher frequency, a shorter wavelength, than the outgoing long wave radiation that the Earth emits, which our eyes can't see. Our eyes are not sensitive to that. So something like CO2 in the atmosphere will absorb photons of long wave or terrestrial radiation that is emitted from the surface and moving outward. It will heat up itself and it will emit that in all directions. So when it absorbs the photon, the molecule of CO2 gets excited. It manifests as a higher temperature. It itself radiates more radiation in all directions, some of which goes back down to the surface and increases the radiative load at the surface. That's the process by which greenhouse gases in the atmosphere, in effect, trap heat within the atmosphere and radiate it back down onto the surface, increasing the amount of energy at the surface. So when we increase the levels of CO2 and nitrous oxide and methane and chlorofluorocarbons in the atmosphere, these gases, which are these types of selective absorbers, contribute to the greenhouse effect, and they increase the planet's surface temperature as well as some of the atmospheric temperature. And what you're looking at here is a 800,000-year history reconstructed from ice cores taken in Greenland and Antarctica of CO2 in the atmosphere. So the glaciers accumulate from snowfall, and as that snow falls, small bubbles of air get trapped as the snow compacts and forms into ice. And when they take an ice core, say at Antarctica, and they drill down, they're drilling down through time. And they can actually date it through isotopic dating processes that they use. and they can also measure the amount of CO2 in those trapped bubbles of air. And they can do that to reconstruct this record right here that shows you how much CO2 was in the atmosphere at different points in time. And you can see there are lots of oscillations here, typically between about 180 and 280 parts per million of CO2. Those oscillations seem to have certain cycles of about 20,000, 40,000, and 100,000 years that match variations in how the Earth orbits around the sun. And additional proxies have been used to reconstruct temperatures to suggest that the temperatures have fluctuated pretty much in concordance with those changes in CO2. Now, the concerning part, of course, is all the way over on the right, where once we hit the Industrial Revolution in about 1750, things take off. And instead of staying within this envelope of roughly 180 to 280 parts per million, we have an excursion, and we've now gone up, and we're above 420 parts per million. We know that the CO2 is changing the energy balance of the atmosphere and contributing to the warming of the planet. And we're seeing the consequences of that in these increased temperatures that we see.
Excuse me, Jeffrey.
Yes.
What causes the dips?
The dips that you see there?
Yes.
So that's orbital variation. So the Earth, when it moves around the sun, has a couple of three, in fact, changes. These are called Milankovitch cycles after a Serbian mathematician and astronomer. And what they have to do is how the Earth is in relation to the sun. So the Earth's rotation around the sun is not circular, it's elliptical, but the size of that ellipse varies on a 100,000-year cycle. And that's one of the variation patterns you see there. There's a strong 100,000-year periodicity within the wiggles that you're seeing there that makes it go up and down. In addition, the Earth is tilted. It's not vertical, perpendicular on its axis. It's actually tilted at about 22.5 degrees relative to the sun. But that doesn't stay that way. That actually moves back and forth at about a 41,000 year periodicity. And that is actually strongly reflected in this if you do a spectral analysis. And in addition, the Earth precesses, which is, if you ever spin a top and you watch it go, and sometimes it will start its spinning and it'll start to then rotate around on its point in a circle while it's spinning really fast. The Earth does that as well. And it does that at about a 22,000 year periodicity. And that too is reflected there. So those periodicities are known to change the amount of solar radiation that comes into the Earth's atmosphere and out. However, they're not large enough to actually make the fluctuations that we see in temperature when we reconstruct the temperature record through paleoclimatological analyses of all sorts of records, ice cores, mud cores, caves, geologic records, etc. So what is believed to happen is that there are amplifications taking place within the Earth's climate system. And that is that there are feedbacks within the system that will exacerbate a warming or exacerbate a cooling. And we have ideas about how that happens, but these are also very concerning because they can lead to feedback. So let me give you an example that's kind of intuitive for our modern day right now. So we have an increase in CO2 in our atmosphere, and that CO2 is known very well from first principles to affect the radiative balance and to result in a warming of the atmosphere and the surface of the Earth. Now, if you warm the surface of the Earth, those warmer temperatures are going to result in less snow and ice accumulation because on average over a very large planet, less time of the year will you be able to have snow develop and snowpacks to be there. Less Arctic sea ice, maybe melting of mountain glaciers, less of a snowpack on the tundra, less, maybe melting of Greenland and Antarctica to an extent that we haven't gotten there, right? Now, the snow itself, by virtue of being white, reflects at the dominant wavelengths that the sun imposes radiation on us, okay? And by reflecting that radiation, It isn't absorbed by the Earth. It is bounced back out to space. Now, if we have less snow and ice, we are going to have a lower albedo, meaning less of the sun's radiation will be reflected out to space. So in addition to the CO2 trapping radiation in our atmosphere and radiating it back down to the surface, we're now reflecting less of the solar radiation and absorbing more of it. So now more solar radiation is actually being absorbed, which means you're going to have even warmer temperatures, which means more of the snow and ice is going to melt, which means the albedo will drop further, which means you'll absorb more solar radiation, which means even more greater temperatures will manifest, and you'll go more and more and more. And you can say, well, that's just going to keep running away, and we're going to lose all our snow and ice. And the answer to that would be yes, that would be the logical extent over many, many years of what would happen because of this snow albedo feedback that takes place. At the same time, within the atmosphere and climate system, there are many other feedbacks. There's a water vapor feedback, there are cloud feedbacks, there are vegetation feedbacks. Some of them are positive and some of them are negative. And how those feedbacks, which are nonlinear, compete with each other to exacerbate or diminish the forcing imposed by these increased greenhouse gases in our atmosphere is where our uncertainty in how much the planet will warm, how it will stabilize. That's where the scientific uncertainty lies. So historically, the climate has moved up and down in temperatures, going way, way back in time. It's thought that the Earth about 500 million years ago, not 500,000, 500 million years ago, and at about 750 million years ago, was basically a block of ice. That changes had taken place, that there had been a runaway freezing almost. And this actually greatly impinged on life on Earth, so that only in the equatorial regions was there open ocean and was life maintained. Now, obviously, this is very early on, very early before the development of the dinosaurs, as we think, and what happened at the KT boundary and all that stuff. But the Earth's history is actually very fascinating. There have been differences over very long geologic timescales in how much energy the sun is emitting, in how much oxygen and CO2 are in the atmosphere. And those differences mean that the way the planet achieved its energy balance could manifest in different ways. Now, when we talk about the last 800,000 or even 5 million years, we're really talking about something that's very similar today, where we have 21% oxygen, where CO2 levels were between 180 and 280 parts per million, where we weren't a block of ice, where we're looking at the conditions that were taking place that are grossly similar to what we see today. Now, that doesn't mean there weren't differences. If you go to the Fertile Crescent in Mesopotamia, that used to be truly fertile. It was much greener there in places like Iraq and Syria than what you see today, where we think of it as very dry and dusty and not as conducive to agriculture because of the lack of water. So there have been changes that have taken place over the era of human civilization, just the last 11, 12,000 years in our climate that are, from our perspective, quite pronounced. Am I answering your question? I tend to go on, so let me know if that was helpful or if there are any further questions you have based on what I said.
Very nice. Thank you.
All right. Okay, so in the here and now, what are some of the manifestations that we are seeing as a result of climate change? Well, one of the things that we're seeing is an increase in the frequency and an intensification of extreme weather events. We're seeing more heat waves, more pronounced elevated temperatures. In South Asia, Australia, the Middle East, they're seeing excursions where temperatures are hitting 50 degrees Celsius with regularity. It's not like unheard of, and they've had extended periods in all those areas where they've had temperatures above that mark. 2 summers ago in 2023, in the Persian Gulf Airport, which is in southwestern Iran, they recorded a heat index, which if you may know, a heat index is actually a combination of temperature and humidity to give an estimate of what the air feels like, of 66.7 degrees Celsius at the surface. That's 152 degrees Fahrenheit. They couldn't fly airplanes. And you can't be outside in something like that. That will very rapidly result in thermal dysregulation and heat stroke in individuals. So the whole airport had to be shut down for an excursion like that. We're seeing events that we'd never seen like that before, of increasing frequency and intensity. We're seeing droughts. We're seeing extreme storm events and very powerful hurricanes, which now seem to have more energy as well. Other consequences include sea level rise. So as the planet warms, the oceans are warming as well. Now we think about solids and liquids as being incompressible. You can't actually, like a balloon of air, you can sit there and you can squeeze on it. You warm it up, it'll expand. You cool it, it will shrink. And we don't think about liquids like water doing the same thing. The ocean is really huge. And in fact, they are slightly compressible liquids and slightly expansive. Solids are too, but less so. And so for something as vast as the ocean, if you increase its temperature as it has by tenths of a degree, it will actually start rising. It will increase. And in fact, sea level has risen considerably over the last 100, 150 years by almost a foot, almost all due to thermal expansion. When Superstorm Sandy hit New York City in 2012, there are seawalls in southern Manhattan that were overtopped. And I'm not going to get the number right, but I think the seawalls were constructed to be 9 feet high. That was a long time ago. By the time Superstorm Sandy came in 2012, they were in effect only about 8 feet high because sea level had risen up. All right. Now, the big concern, of course, is what would happen if we have a melting of Greenland and Antarctica. Greenland on its own represents about 6 to 7 meters of sea level rise. If you melt all the ice there and put it into the ocean and distribute it, on average, it will rise about 6 meters. Antarctica is more like 55 to 60 meters. It's massive. And there are some areas of it, such as the West Antarctic ice sheet, which is itself about the size of Greenland, about 6 meters of ice, that's very concerned that it will just break off. And if it does, it would be catastrophic because it would raise sea levels about 6 meters. On the left, you're seeing something that shows South Florida. And you can see a map in the middle, the one on the right there showing South Florida, that shows what would it look like if you had 5 meters of sea level rise and if you had 10 meters of sea level rise. And with 10 meters, you can see most of South Florida is gone. Obviously, South Florida is very, very flat. Now, already, if you look at the lower right, you see flooding in the streets of Miami. That flooding is not induced by rainfall. There was no rainfall that caused this. This is tidal flooding. And you may say to yourself, well, why don't they build a seawall? And the reason is seawalls don't work in South Florida because South Florida is predominantly limestone. And limestone is a very porous stone that produces a lot of conduits under it where water gets in. And this water is actually not overtopping the beach and coming over. It's actually percolating up underneath and rising up through the limestone and flooding the streets. So you could build a seawall, but it's not going to stop the sea from going underneath that and percolating up. A big problem that they have in Miami. That's not nearly as large as the problem for some of the island nations. This is Kiribati in the Pacific. It's 1 to 2 feet above sea level for this entire atoll nation. And so for this nation state, a rise in sea level is an existential crisis for them. If sea level goes up high enough, there's no way they can continue to inhabit this without some radical feat of engineering, which might be a very questionable purpose. So you would have stateless people induced by this who would have to move elsewhere, have to be taken on by some other country, and obviously a whole culture and way of life would be lost. Another manifestation that we're seeing as a result of climate change is an increase in wildfires. Areas that we're used to a certain amount of precipitation, maybe seeing less of it, or maybe getting it more episodically, and there are higher temperatures there. The consequences of this are that the increased temperatures and the changes in the hydrologic cycle are producing more kindling and fodder for wildfires. You can imagine this certainly for some place like California or the West more broadly, which tends to be arid to begin with, that vegetation now dries out. It's more capable of burning faster. There's more dry brush. If they have episodic rains that come through, the desert blooms, so to speak. And then when it dries out and gets really dry, all that dies off. And you've got all this surface brush that can act as fuel for fires. And we've seen a lot of this every year, every summer. We're really seeing a lot of fires. We saw huge fires in LA a while ago. This is a shot on the right of one of those, a house in Los Angeles burning from a year ago. And, you know, it's pretty cataclysmic. There obviously are dangers associated, destructions of ecosystems, loss of wildlife, and there are risks to human life. Of course, people can be asphyxiated, they can be burned and trapped. There are also more slow creep effects that have to do with our respiratory health. Wildfires produce a lot of inorganic gases, hydrocarbons, and oxygenated organics, most of which are not particularly good for us to breathe. A lot of this stuff is classified as what we call PM 2.5, which stands for particulate matter of 2.5 micrometers or smaller. And we classify it by size because the size, whoops, I don't have that slide there, but the size of the particulate matter determines how deeply it can penetrate into our lungs, whether it gets into our alveolar sacs, where the air exchange occurs into our blood system, and whether it actually enters our blood system. So things that are very small do that penetration. So you can even have ultra fine ones that make it in very quickly, but anything below 2.5 is going to get very deep in the lungs. And what you see in the graph on the left is it shows before, during, and after 4 different wildfires that took place, measurements of particulate matter, and you can see how you have elevated excursions there. And these cause a lot of respiratory problems. There are increases in hospitalization visits, increases in cardiovascular events, increases in all-cause mortality have been demonstrated to take place as a result of wildfires. We see this in the hospital visits and the amount of deaths that occur during and immediately after wildfire events in localities. Another big concern that takes place about this, and you know, this is not an exhaustive list I'm giving you here, is what happens to food security. Obviously, if we have changes in our climate, in the regularity and the reliability of our temperatures and the rainfall that's delivered, that has consequences for our ability to actually husband animals and grow food. And this has been really central to human civilization becoming stationary, moving away from being nomadic and settling down. We'd settle in locations where you have reliability. So you know you can grow your crops and you can grow them to an extent and you can feed a certain amount of people that you're able to ultimately see and grow to. Throughout human history, and there are scholars that have argued this, that civilization collapses may be often triggered by changes in climate that actually impinge upon water and food security and cause so that a civilization can't continue to be where they have settled. Another big one is conflict. And this is a more complex phenomenon. I mean, food security gets complicated as well, but this really is one for which climate is only one of a number of stressors. And so I'm going to give you an example of Lake Chad. So Lake Chad is this international lake that spans across 5 countries in Central Africa. It actually has another 6 countries with river systems that fed into Lake Chad. And Lake Chad was a very shallow lake. It was not particularly deep, and it was used for fishing. And what happened is that there's a drying in the Sahel, which is the band of region below the Saharan desert in Africa. And that's due to some variability and some climate change taking place. And that resulted in the lake receding and getting smaller, particularly from its northern edge, which is where it was extending into the Sahel. And the people there who had relied on it for fishing no longer had water there, but the lake bed was very rich soil from all the biological activity that was there. So they switched from fishing to agriculture as the lake was exposed. But of course, if you're going to do agriculture, you need water. And because it's a dry, arid area, the place where they got the water was to siphon it off of the retreating lake. That accelerated the reduction in the shrinkage of the lake. And you can see on the top the extent of it in 1973, and then you can see the extent of it in 2017, and there's almost nothing left. Now, in addition, this is because it's transnational, a place where national governments have disagreements and may get very hostile over this very important resource for them. It is also because it's post-colonial and the borders there are really artificial in many sense. There are many different tribes in the area, and they're also going to fight for the resources. There are also different religions in the area, and they also fight for the resources. So a climate stressor, transnational issue, tribal issues, post-colonialism, differences in religion, and you have a cauldron where there has been a tremendous amount of conflict. And I'm not going to tell you that climate is the cause of it, but it's one of the stressors that is contributing to the problem that we see in this area. Okay, so the planet is warming, the climate is changing, and it has many effects that are impacting human well-being and ecosystems and our health. And it was under that recognition that Columbia University decided that it was time to build a climate school. And this wasn't born out of a lack of history of work in this field. As a matter of fact, Columbia has a very long, rich history in working in earth environmental sciences, climate, and sustainability. I'm going to tell you a little bit about that because that frames how we got to building a school. So there are many climate-related achievements at Columbia. We have over 1,000 researchers working on climate-related projects. It is an enormous number. It's probably more than any other institution in the world, and it's been that way for a very long time. The term global warming was actually coined by Wally Broecker, who's a geochemist. He died about 7 years ago at Columbia University. He wrote a paper in 1975 asking, are we on the brink of a pronounced global warming? He was anticipating that we would start to see that rise in temperatures that took place in the 70s, began in the 70s. We also have over 5,000 alumni from bachelor's and master's programs in climate and sustainability related programs. We're the #1 US university in contributions to Intergovernmental Panel on Climate Change reports. And we've had 26 scientists named to Reuters' hot list of 26 climate scientists. Our leadership in climate science research extends back decades. In 1949, Mike is wearing a Lamont Open House t-shirt, I noticed, or sweatshirt. The Lamont Geological Observatory, as it was originally called, was founded. And you can see over this timeline a number, though certainly not nearly an exhaustive list of some of the accomplishments that were developed there. In 1956, Ewing and Dawn established the natural cycles that can trigger the onset and termination of ice ages, which is what you were seeing in those wiggles in the ice cores. Those were the ice ages and the retreat of them in those 100,000-year cycles. We actually put a seismometer on the moon with the Apollo 11 mission. Wally Broecker, there you can see him, coined global warming in 75, built a comprehensive world seafloor map. 1988, Mo Ramo authored the uplift and weathering hypothesis that links Himalayan uplift to long-term CO2 cycles and global cooling. There was Paul Richards and Song discovered the Earth's inner core spins slightly faster than the mantle. There was an international polar year that Robin Bell was instrumental in leading, looks at ocean acidification rates, climate change and the Syrian conflict were examined, subglacial meltwater, and the deadly effects of heat and humidity on human health. That's just some of it. There's also El Nino predictions. The first ones came out of Lamont. There's also being able to understand what's known as the thermohaline circulation and tracers in the sea, Wally Broecker's work, because he did a lot of seminal work. So we played a critical role through the Lamont Doherty Observatory of providing evidence of human-induced climate change. On the left shows a map of our seafloor core that have been taken by Lamont cruise vessels and are stored at the Lamont Doherty. These are cores of the subsurface of the ocean. that provide records of what's going on, and it's one of the largest cores in the world, and it's ongoing. As whenever the ship is out, it takes cores on these on its vessel, on its trips, on its transects to develop it. And then, of course, you see something that's one of these reconstructions over 800,000 years with just a different graphic showing you CO2 and CO2 today, that same graphic we were looking before, and then estimated temperature changes that were from proxy-based reconstructions. And you can see how those match what we see in the fluctuations of the CO2 cycles. Now, Lamont Doherty was launched in 1949. There was what was called Lamont Geological Observatory. The Dohertys contributed money and became the Lamont Doherty Geological Observatory, then the Lamont Doherty Earth Observatory. And in 1975, a decision was made to launch an Earth Institute. And that was to bring together units across the university to address issues of sustainable development. And it acts as an umbrella organization spanning all the schools in the university. And the idea was to actually advance interdisciplinary research that would bring together earth scientists with economists, with financiers, with public health officials and researchers and clinicians, with built environment architects, with engineers, and with historians. The idea was to bring them together so that in a transdisciplinary way, they could address challenging multidisciplinary issues. That institute was around for a while. I'll give you one example of something they did. It's less climate involved, but early on, some geochemists and hydrologists at Lamont partnered with some environmental health scientists and epidemiologists who studied toxicology. And they won a Superfund grant from the NIH to study arsenic poisoning in Bangladesh. So in Bangladesh, they used to suffer from these enormous outbreaks of cholera. Bangladesh, much of it is a very flat delta of these major rivers, the Meghna, the Brahmaputra, and the Ganges all converge there. And there are enormous flooding events that take place over the delta, where parts of the cities and towns are just completely flooded sometimes when these events take place. And historically, people drew their drinking water from surface waters, but surface waters can be contaminated. And in a place like that, which is in the subtropics, something like cholera can be very problematic. And they would have very large cholera outbreaks, which would kill many, many people. And in the 60s and 70s, the World Health Organization came in and said, look, you guys need to dig wells. If you dig subsurface wells, you're going to be getting water that goes through the soil matrix and will be filtered of all living organisms. And as a consequence of that, you won't get cholera. So they did that, and it enormously controlled cholera. But what they didn't know is that under parts of Bangladesh, there are naturally occurring veins of arsenic that's labile. And so what ensued was slow poisoning of segments of the population. They would develop elevated cancer rates, certain types of organ failure, what's called arsonitosis. And so this Superfund project was designed to try to understand what were the manifestations of the disease, but additionally, what's the geochemistry going on that is making this arsenic labile and mobile and active? And how do we map it and find places where they can dig well water that is not contaminated with arsenic? And that project went on for more than 25 years. And it still continues today, not directly with the climate school and Columbia as of now. The leader of it, Joe Graziano, retired, but it's an example of the kind of transdisciplinary research that the Earth Institute really was fomenting. However, in about 2018, the idea of building a climate school was put forth, and a task was put together to decide whether this was a good idea. It was recommended, and in 2021, the Earth Institute was transformed into the Climate School. From its conception, it encompasses all of the Earth Institute. And by placing the Earth Institute directly in the Climate School, it harnesses Columbia's academic firepower in the spaces of climate, sustainability, environment, and Earth. So this just has a short timeline of the early development. It was actually announced in 2020. We announced our first master's program, which was an existing master's program that the Earth Institute had operated in partnership with the School of Arts and Sciences. School leadership was announced. The first students matriculated in September 21. University fully approved it, and the trustees approved it, so it became official at the end of 2021. We have a number of mission statements. We're revising them. I'm actually the senior vice dean, not the dean of the climate school. And our dean, Alexis Abramson, started in January, and she has been developing a new mission and vision statement, as most deans do, that aligns with how she wants to move forward with it. And you can see, one of the phrases we have is that without intervention, climate change will reshape our planet through rising seas, extreme weather, and collapsing ecosystems, threatening the health, security, and livelihoods of billions around the world. So we have work to do, and of course, join us. The Climate School is a model for a new paradigm in higher education. Climate and Earth are central to our mission and actions. We're hyper-focused on the world's pressing problems in that space. At the same time, we have interdisciplinarity under one umbrella, meaning one school. We have educational programs and research that embrace the intersection and importance of multiple disciplines. That research is science and solutions focused. So we want to move out of the ivory tower and build transformational research that's not merely basic, though that is important and we will continue it, but also translational research. And if we build translational research, we have to have an emphasis on impact. We have to move those into the marketplace, into policies, business models, healthcare solutions, et cetera. In other words, we have to partner with people outside the academy, corporations, government, NGOs, international organizations, in order to advance the findings that we may have. And I'll tell you about some of those findings in a bit. So what we do is, we certainly source initiatives. We have research and strategic partners that we're building out. We are a school in building still. We design solutions. We have something called the Action Collaboratives to do that. We're looking to deliver and scale impact. We have something called the Global Impact Lab, which is to help researchers and students build those partnerships with those outside entities and have impact, whether it's partnering with a school or partnering with a municipality or partnering with a wastewater treatment facility or partnering with a corporation. These are the types of things that the Global Impact Lab is trying to improve. Now, one of the things we have to do is mitigation. We have to reduce, avoid, or sequester greenhouse gases, and that involves a heavy emphasis on technologies, both natural and technological, that will capture or reduce the amount of greenhouse gases that we produce or need to be captured. We also have to improve our adaptation and resilience, which means strengthening vulnerable communities and ecosystems. And we also have to educate. We have to train climate leaders. We have some priorities to achieve impact, and these involve some multidisciplinary teams from across the school, the university, and with diverse partners outside, where we are pursuing those real-world solutions. And these are in our first 5 approaches: focus on food and nourishing humanity in a changing climate, energy, accelerating an equitable energy transition to a net zero carbon energy economy, water, ensuring clean and healthy coastal, ocean, and freshwater systems, the built environment. We are in the built environment, of course, based in New York City. So we want to transform the cities where 6% of the world's population lives at this point for equitable, low carbon, and climate resilient futures. And we need to strengthen resilience to disasters. This is also reflected in our educational programs. We have master's degree programs. We have undergraduate degree offerings. We are building out executive education, which we've done some, but we're building out more, as well as K through grade programs. And we're working to build out a doctoral program. Just to give you some example, we have our largest activity in the master's space. We originally had a master's that we brought over that I mentioned from Arts and Sciences. This was a 1-degree Master's of Arts and Climate Society program. This fall, we launched 2 new programs. One is a Master's of Science in Climate. This is a 2-year program where everybody in it learns and gets their bona fides about climate, its dynamics, the justice issues, mitigation, adaptation, the legal aspects, maybe some finance associated with it. But they also learn about something else. We want people who are going out who know both about the climate system, but about some other system so that they can bring that together and be communicators in the world to solve problems in particular sectors. So they either get this by getting an advanced certificate, which is a New York State certified credential, has to be approved by NYSED, the New York State Education Department. We have 3 of those. One is in disaster management, others in food systems, and others is in systems and analytics. We're hoping to build out another one in the energy transition. And in addition, there are other opportunities where instead of an advanced certificate, you get a dual degree. And we have partnerships with the engineering school where they can get a master's in engineering in carbon management as well as this MS in climate. That's one dual. And the other one is with our School of Architecture, Planning, and Preservation, where they study the built environment. So they study climate and the built environment. In addition, we also have a separate degree that we built out with Columbia's Business School for a Master of Science in Climate Finance. This is a 1-year program where students take courses both in the climate school and in the business school. In addition, we have some partner programs. These are left over from the Earth Institute. Some of them we're more engaged with than others, and I'll leave it at that for that. Our faculty is growing. That's our Dean, Alexis Abramson. She alphabetically actually comes first, and there she is in the upper left. And at this point, we have 34 faculty, I believe you're looking at here. Yes. We've been expanding from that over the last 4 years when we had basically 7 of us initially. I'll note that Christina Douglas, who's in the upper column towards the right there, she is an associate professor who's an archaeologist, anthropologist, environmental scientist, historian. She just was awarded a MacArthur this week, which is one of the Genius Grants for her work. So we're very proud of that. The Earth Institute, as an institute, had an enormous number of centers that were built in it. And this gets a little bit into the details how a university operates. But at Columbia University, the schools are entities that can confer degrees and appoint faculty. But as an institute, the Earth Institute couldn't do that. Whenever it wanted to offer an educational program, it had to partner with a school in order to build that, because the school then had to confer the degrees. And those are those partner programs the 2 slides ago I mentioned. Within the Earth Institute, there are a lot of centers. One of them is the Lamont Doherty Earth Observatory, which is massive. It has almost 500 people on its own campus in Rockland County, New York, outside New York City. The others are not as large. They range in size from 5 to up to 40 people in them. But you can see that there are a whole variety of them. There's some that are at Lamont, including the Center for International Earth Systems Information. There's some that are based on the Morningside campus where Columbia proper is, such as AC4, the Advanced Consortium on Cooperation, Conflict, and Complexity, and the Center for Sustainable Urban Development, and the Lenfest Center for Sustainable Energy. These are all based within the climate school. In addition, we have a lot of affiliated centers. Very often the affiliated center's lead is a faculty member jointly appointed in the climate school. So the Sabin Center for Climate Change and the Law has been affiliated with the Earth Institute for a long time because Michael Gerard is part of it. He's also faculty at the law school and jointly at the climate school. The Center for Global Energy Policy, Jason Bordoff, is appointed in SEPA and in the climate school. Same with the Columbia Electrochemical Center, which builds out better batteries. Alan West is jointly appointed in the engineering school and in the climate school. And the Center for Resilient Cities and Landscapes, Kate Orff, is appointed in the School of Architecture, Planning, and Preservation and in the climate school. So I'm going to tell you a little bit about these centers, a few of them and what they do. The center, CESIN, the Center for Integrated Earth System Information, they've done a huge amount of work with the Intergovernmental Panel on Climate Change. They did a lot of work for NASA. They do geospatial mapping and support where they try to figure out where settlements are in developing nations so that that can support public health initiatives, demographic understanding, water infrastructure build out, education, et cetera. They're big proponents of open data science and map development, and they have a lot of projects studying climate mobility. Somebody wanting to ask a question?
Not certain if anyone has a question, but we have had Alex DeShervin talk in Earth to class.
Wonderful. Wonderful. And I'm not going to be able to go into nearly the detail he did because I have just this slide, and I'm going to move on because I'm just going to give you an overview of a number of the centers. Another one is the Center for Climate Systems Research. This does a lot of global climate modeling, trying to understand processes, land surface interactions, the impact of clouds on global warming, trying to understand how the stratosphere regulates our climate system, as well as work that's more applied, looking at food security and what is happening in that space and a variety of climate impacts. At Lamont, there are many, many research projects. I just picked one here. This is work that's been being led by Bejan Yan, and he's been looking into micro and nanoplastics in our air, water, and soils. He's helped develop the use of hyperspectral stimulated Raman scattering imaging, SRS, which allows them to quantify nanoplastics within waters and air. And he's studying the bioaccumulation of that in organisms, and particularly in humans, in our organ systems, and the health consequences of this. You may have heard that they now estimate that the average adult of some age has a teaspoon of plastic in their brain. And trying to understand the consequences of this is something that we're really going to have to understand because the plastics are highly persistent and they're accumulating within our biology and our ecosystems. One of the big areas that they're looking at is the shedding from laundry. Laundry, a lot of the fibers that go into the fabrics that we wear are not natural, they're synthetic, and they get fragment off in micro and nano sizes, and they go into our water systems. And if we can figure out a means of actually capturing them, consolidating and safely disposing them, there'll be less of them floating around in our rivers and certainly in the air and soils and our food as well. So this capture and reduction is something that they're trying to study and hopefully engineer. Then there's engineering solutions to development issues, and this is something Quadracci, Sustainable Energy Engineering Lab, which is led by Vijay Modi, does. They do a lot of work in sub-Saharan Africa and in India. They look at the use of shared solar panels in rural situations, leveraging data to improve energy investment, so they can figure out where and when to turn things on and off and provide access. Electricity access and planning is a big portion of this, as well as figuring out things as simple as acacia irrigation and how to maximize and do that and efficiently in places where water is a critical and limited resource. The Columbia Electrochemical Energy Center I mentioned, led by Alan West, they look into batteries and fuel cells and electrolyzers. They are finding new materials and means for storing energy, and they're trying to overcome the intermittency of solar and wind power and find ways of storing that energy so that it can be used 24/7, which is a big, important issue as we're moving into a transition to renewable energy. The National Center for Disaster Preparedness looks at a whole suite of issues as to how we can be less reactive and more proactive in our response and resilience to disasters. They're developing things like financial instruments and climate risk for the developing world so that they can actually be financially buffered and be able to deal with the consequences and not be devastated. And that includes climate finance vulnerability, the study of it. They also do a lot of training. They historically, until this year, because of changes in the federal government, have had a huge partnership with FEMA in the US and done a lot of training in disaster response and how to improve efficiency and build things out so that we can actually bring people in and respond more appropriately, but also be better prepared. They also do work on natural hazards projections. Then we have to also build the capital. You know, if we're going to actually get out of the problem and address our climate issues, let alone our climate and sustainability issues, it involves an enormous amount of money. Developing a net zero circular economy, even in part, it's $100 trillion challenge. And it made that maybe, tens of trillions of dollars a year. And that's a lot of money. And that can't be done by universities. It can't be done by philanthropy. It has to unlock private and public capital and new investment and financing tools. And so we have things like our Columbia Center on Sustainable Investment, which does research into mining governance and looking at critical minerals and how they're brought out, but also investment law and policy, sustainable business and finance, and fossil fuel phase out. We're looking into how we can seed investment in the developing world and bring new technologies in, and establish new production circularity business models. One project I'll just tell you about that they're involved with, as well as the Columbia the Center for Sustainable Development, which is led by Jeffrey Sachs, is to this ASEAN project they have, which is to lead the world. ASEAN must pursue and coordinate the financing of a fully integrated multi-sectoral regional low-carbon energy system designed to cut emissions, increase resilience to shocks, and ensure that the benefits of the transition are distributed equitably. So what is ASEAN? Well, it's this Association of Southeast Asian Nations. It is 11 nations spanning, including like Indonesia and Malaysia and Vietnam. It does not include China, but amongst them, they have nearly 700 million people there, these island nations there, where they want to build a coordinated plan, working with the banks, the government, and their energy sectors to develop low carbon energy systems where maybe palm oil is used in some area or biofuel in one, and solar is used in another, and wind is another, and another provides the grids and the electricity wires that may be run from one place to another across nations so that they can build a coordinated net zero low carbon energy system, at least. Very large scale effort to try to do something where that people have talked about for a long time. Well, if one person can provide the water and the energy to build things, and the other can capture the renewable energy, and then the wires can transmit it to nation states, could we do this as a cooperative? That requires a lot of financing, a lot of political cooperation, but the winds are quite favorable and the political alignment is quite favorable across these 11 nation states, and they're trying to see if they can actually build something like this now. And then the Sabin Center for Climate Change Law, I mentioned they do an enormous amount of work. They do energy law, environmental and land use law, international foreign law, climate and business law, climate change litigation, carbon management and negative emissions, environmental justice. They have a climate tracker where they track all legal cases in the US, and they've started doing this internationally. They track what's happened when the government passes a new law or rescinds it. And they also have something called the Renewable Energy Legal Defense Initiative that they've borne out. It's one of a number of sort of initiatives that are like 501c3s. In this one, it's pro bono legal work that can be brought into a community to help them advocate to energy utility boards, community boards, and local governments about building in renewable energy infrastructure. Very often, renewable energy and new grid wirings, new electric grids, or new wind farms, they get bogged down in a lot of legal challenges. And it's not to say that the legal challenges aren't justified and shouldn't be had, but they get bogged down so that the construction of these projects usually is delayed decades. And so their aim here is to accelerate that time scale so that decisions can be made and solutions can be found more expeditiously. So I will stop there. I hope you've learned a few things about what we're doing at the climate school and some of the issues that we're trying to tackle. And I'm happy to take a few questions.
Thank you very much, Jeffrey. One question I have is, what's the connection between the climate school and the global climate centers that Columbia has established around the world?
Right. So those aren't global climate centers. Those are global centers. And so the global centers, they're about, I lost track. There are 11 or 12 or maybe 13. The first one was in Paris. We have one in Beijing. We have one in Istanbul, a new one in Athens, Rio de Janeiro, Santiago, Chile, Amman, Jordan, Nairobi. So these are centers that are sort of outposts for Columbia University. Some universities have built out schools, like NYU built out schools in Abu Dhabi. They have another one in Shanghai, and they built out separate campuses where they're doing almost isolated educational programs. We haven't gone that way. The decision was not to do that, but to have sort of places where scholars can convene. Now, some of the centers are focused on particular topics, like the one in Istanbul is particularly focused on the humanities. Others are more focused on science, and some of them are broader. And these are places where scholars can come together, where we can have convenings and we can hold events. So we've certainly partnered with them. The one in Rio de Janeiro, we worked with that center to help launch a Rio Climate Hub, which was done with the mayor's office down in Rio de Janeiro, to actually promote businesses into thinking about ways of building out more green and sustainable energy portfolios in how they conduct their own business, both in-house and in the products they produce, for instance.
Yeah, I worked with someone from the Rio and the university in Chiamanchina. We had a program
Wonderful.
a couple of years ago.
Yeah. So we interface with them. The global centers are led by Wafa El Sadr, and we partner with her on efforts when we can. Obviously, there's time and resource limitations, but the global center's focus is not exclusively climate. It's broadly for the whole university.
Okay, thank you. Anybody else?
All right.
Thank you very much. Very interesting.
Yep. No questions. They all have a very wonderful weekend, and I wish you all well. All right.
Thank you. Stay dry, everybody.
Take care. Bye.
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 Okay, for those of you still on, the next Earth to class will be in 2 weeks. We're going to welcome back, if I got it correct, let me just check. I think we're having Ajit Subramanian back with us. Yes, we have Ajit talking about the emerging threat of harmful algal blooms in the Arctic. Then after that, we'll get Kirsten Leonard about big data sets. So after that, it spreads out again. But thank you very much for coming.
Thank you, Michael.
Okay, have a good weekend, everyone.
Okay. Sure.
Bye all.